Okay, so welcome back, guys. We have finished the derivation for electric field at an axial line due to a dipole. Now we'll look at the equatorial line. So what does that mean to be the equatorial line? It is a line which passes through the center of the dipole perpendicular to the dipole. So if this is the dipole, the equatorial line is the line which passes through the center perpendicular to the dipole. So now if we need to find the equatorial electric field, on equatorial plane or line. So to find the electric field, let's first construct the dipole. We have a positive charge and a negative charge separated by distance 2L. So I'll just separately write it as L and L. Now we have to consider this equatorial line and a point P. The electric field at point P is going to be the individual contribution due to positive and negative charges. As I already said that when we consider a point P, it means as if we are bringing a test positive unit charge. So that means this is positive in nature, and positive repels. So the electric field due to this positive charge is going to be in the line joining the two charges but away from it, because positive and positive repels. So it's going to be this way. This vector is the electric field vector of the positive charge, and the negative charge is again going to attract this positive charge because it is negative and positive in nature. So you're going to get an electric field in this line of force in this way. So these two are the electric fields. In the previous case, it was much simpler because both the electric fields due to the dipole were along the same line. That is, this is the point P. One had an electric field in this way and the other had in this way. You can add them algebraically because they are along the same line. But in this case, we know that electric fields are not in the same line. We cannot add them, just numbers. So here we need to do vector addition. So we can either use two methods. That is, one is using the formula for a resultant vector, which is net vector E is equal to root of E1 squared plus E2 squared plus 2E1 E2 cos of the angle between them, phi. This is the formula for resultant vector of any two vectors. This is one of the methods, or the other method is to resolve the component of this vector along the line and similarly this vector along this line and then add them together. I prefer this method because it makes more sense. In this case, we'll have to assume that the opposite vectors must cancel off each other, whereas this is a more general case which can be applied to any derivation. So let's go ahead with this method. So we can easily find out E1 and E2, but we need to find out the angle between them, and that's the major task. So how do we find the angle between them? First, we need to assume an angle, which is this angle, theta. And let's also assume the point P is at a distance x from the center. In the previous case, we assumed distance x from the center over here at the axial line. Now it's on the equatorial line. So we have all the variables we need. That is the distance from the center and then the angle which the vector makes with the base. So let's proceed. Let's individually find out the electric field's magnitude. So electric field's magnitude due to the positive charge is K plus Q, as in K multiplied by positive Q. I'll just name it over here, plus Q and minus Q. These are the two charges. So K plus Q, it is not addition, it is multiplication with the positive of Q, divided by the distance between this charge and the point, which is the hypotenuse of this triangle. So what is the hypotenuse of the triangle? It's the root of the sum of the other two sides. So it is the root of x squared plus L squared. And that's the same case over here. So this is going to be, the formula for electric field is kq by r squared. So it's going to be this distance squared. So the root cancels off. So you get x squared plus L squared. This is the magnitude of the electric field. So you can avoid the positive symbol and it just becomes Q. This is equation number 1. Now let's find the electric field due to the negative charge Q. By symmetry you can already say it's going to be same, but let's do it. So the negative charge is again K, Q, it's minus Q but we are looking only for the magnitude, by the distance is going to be the same and you're squaring it, so the root cancels off. Equation number 2. So E plus and E minus have the same value. So you can treat both of them as just E. Why? So that we don't have to complicate the process. Let's just take E plus equals E minus equals the electric field E. We can use this direct substitution in the formula. So now let's go ahead with the resultant vectors formula. So since we have the individual vectors, now we know the formula for resultant vector, which is E plus square plus E minus square plus 2E plus E minus cos phi. And we have just seen that the magnitudes are same. So let's just take E plus and E minus as E. And later we can substitute the value at the final answer. So you get E square plus E square plus 2E into E is again E square cos phi. This angle phi is the angle between these two vectors and not this. Phi is always the angle between the vectors which you want to add. So how do we calculate phi? Let's see. So I'm going to rub off these two parts. This angle is theta. So in this triangle P plus Q minus Q, in this triangle the sum of the interior angles is always going to be 180 degrees. So angle P plus theta, and this is also theta because these two sides are equal, plus theta equals 180 degrees. So what is angle P? 180 minus 2 theta. Since we know this angle, now we can easily find out phi. And how? Because in a line segment, if you have an intersection and if this angle is given to be theta, this angle is going to be 180 minus theta, and this is the linear property. So the same logic applies over here. We know this angle, which is found to be 180 minus 2 theta. So the other angle is going to be 180 minus 2 theta, which is equal to 2 theta. So phi is 2 theta in this case. And let's substitute that in the formula. So E1 square plus E1 square is 2E1 square, 2E square plus 2E square cos of 2 theta. So we have the formula. We can take 2E square common from both these terms to make it root 2E square into 1 plus cos 2 theta. Now I'm going to remove the 2E square outside the brackets. So that's going to be root 2, and root of E square is E. So root 2E into root of 1 plus cos 2 theta. You just need to know two formulas to derive this, and that is one from grade 10, which is sin square theta plus cos square theta equals 1. And the other one is from your grade 11 mathematics, that is cos of x plus y equals cos x cos y minus sin x sin y. So what we have to do is to find cos 2 theta, you just have to write it as cos of theta plus theta. So cos of 2 theta is same as cos of theta plus theta. And why I split it like this is to apply this formula. So cos of x plus y, where x and y are the same, is going to be cos theta minus sin theta, which is just cos square theta minus sin square theta. You can find this out after applying this formula. Now we can split this into two types by substituting either for cos square theta from this equation or either for sin square theta from this equation. So let's see in both the cases what happens. In the first case, we are going to substitute for cos square theta, which is 1 minus sin square theta. So 1 minus sin square theta minus sin square theta, which is of this. And again, now we are going to substitute for sin square theta from here. So this is going to be cos square theta minus sin square theta is 1 minus cos square theta. 1 minus cos square theta. Now upon simplifying this, you'll get two formulas. One is going to be 1 minus 2 sin square theta and the other one is going to be 2 cos square theta minus 1. So now it's up to us which formula we want to choose. So you can just simplify this and you'll find out that the third formula which we require, which we need in this case, is cos 2 theta equals 2 cos square theta minus 1 or 1 minus 2 sin square theta. In this case, we can apply both, but we have to see which one is more simple, which one helps us to finish this problem easier. So the main objective is that if you substitute either this or this, which of this will make this term simpler? So just check it out. Root of 1 plus, let's substitute the first formula. For cos 2 theta, it is 2 cos square theta minus 1. 2 cos square theta minus 1. You get the answer to be root of 2 cos square theta, and the other case is going to be root of 1 plus cos 2 theta is 1 minus 2 sin square theta. So 1 plus 1 minus 2 sin square theta, which is 2 minus 2 sin square theta. So we can see that it's easier to simplify the first term than the second term. That is, this is going to be root 2 cos theta. But for this we need to apply another property. So let's go ahead with the first one. That is, we are going to substitute 1 plus cos 2 theta as 2 cos square theta minus 1. And we are almost there. Root 2e into root of 1 plus 2 cos square theta minus 1. That's root 2e into 1 and 1 cancels off and you are left with root 2 into cos theta. That's because root 2 cos square theta becomes root 2 cos theta. 2 times root 2 is 2. So 2e cos theta. This is the final answer. Now you just have to substitute the values for e and cos theta as how we have shown in the previous place. Let me just write the values of those two quantities. Electric field is the same by both the positive and negative, so we are just going to take the magnitude, which is kq divided by r squared, and that's x squared plus l squared root the whole squared. So it just remains as x squared plus l squared. And cos theta, from this triangle we can find it to be L divided by x square plus L square root of x square plus L square. These two quantities we are going to be substituting here. I'll just start from the beginning. Okay, so the total electric field is equal to 2e cos theta, that is 2kq by x square plus L square into cos theta is L by root of x square plus L square. We're going to take k outside and group 2LQ. And I think you know why? Because 2LQ is equal to the dipole moment. We have discussed this in the previous video. Dipole moment is 2L times Q. This is 2LQ divided by, I'm going to write x square plus L square, the whole root, as raised to half. It's the same denotation. Because root of a is just a raised to half, is the same thing. So why I'm doing this is because it's going to be simply easier for adding these two terms, for combining these two terms. So how we are going to combine is that a raised to half plus a raised to 1 is a raised to 1 by half plus 1. This is just the laws of exponents, right? A raised to m plus a raised to n, a raised to m into a raised to n is a raised to m plus n. So that's what we have done here. And same thing is going to be applied over here, where here a is just x squared plus l squared, the whole as it is, raised to 1 plus 1 by 2, that is 3 by 2. So we are left with kp divided by x squared plus l squared raised to 3 by 2. This is the electric field, but we can simplify again using the same assumption we have done last time. That is, the distance x which we have chosen is always going to be much greater than the length of the dipole, the half the length of the dipole. So it wouldn't make a difference. X squared plus L squared is still going to be approximately equal to x squared. As I have shown the example, it's like adding 50 squared and 0.002 squared is still going to be somewhere around 50 squared. It's not going to make a big difference. So we're going to write x squared plus L squared as x squared. So you get k cube kp divided by x squared raised to 3 by 2. So how do you simplify this? A raised to m into n by m. It's of this form, a raised to m into n by m. So this is same as, for example, a squared to 3 by 2 is a squared into 3 by 2. You can multiply the powers. So in this case, when you multiply the powers, you're going to get a raised to m into n by m, which is a raised to n. So that's the same thing we're going to do here. The squared is going to get cancelled off by the denominator and numerator. So you're left with kp by x cube. And this is the final answer. The electric field at an axial line due to a dipole is 1 by 4 pi epsilon naught dipole moment by x cube. This is the electric field with the condition that x is far greater than L. If you have gotten a numerical in which x is not greater than L, for example in a question if it's given x is 20 centimeter and L is 10 centimeter, then you cannot apply this condition, and over there you need to go ahead with this formula. So it's better to remember this and from here to come to arrive at this conclusion at the spot. So this is the final equation, and the direction of the electric field is always, the reason why we took only the magnitude here and not the symbol while doing these calculations, you realize that we took E plus equals E minus equals E. And the reason why we took only the magnitude is because we have already considered the direction. So now we need only the magnitude to determine the final answer. The direction can be found out by just applying the logic which we have done. Positive and positive repels, positive and negative attracts. So the resultant of this electric field is going to be somewhere between these two, right? So this is how the electric field is. The net electric field is going to be towards the direction of the negative of the dipole and with a magnitude of this. So this is the electric field due to the dipole at an equatorial point. After this, we'll have to do how the electric dipole would behave in an uniform electric field. And then we'll be done with electric dipoles, and there's a last part in this chapter which is known as the Gauss law, Gauss theorem. So I'll see you all in the next videos, and stay tuned.